So I promised I would record class today, and I didn't. Sometimes it records automatically, sometimes it doesn't. So I did not hit record, but I have 20 minutes until my next class. So I thought I'd pop back into this classroom and make a video, at least doing an overview of what we did in class, and definitely making sure you have the information you need before the test on Monday. Which, by the way, another thing that I did in class today is I asked everyone to tell me if they would prefer to take Monday's test in person in the classroom on Monday, or if they would prefer to do it remotely with their camera on and take it synchronously remotely. So if you were not in class and were not able to respond to that today, please shoot me an email and let me know. I think I have like 6 more spots for people to come in the classroom if you would like to. So anyway, we started with this on the board. If factors come in partners, can a number have an odd number of factors? So that was kind of the, think about that question as, students were coming into the classroom. And where we left off in the last class was we were looking at, oh no, where's my handout? Oh, wait, here it is. We were looking at, it's all scribbled all over here. We were determining whether this number 269 was prime. And we decided that we only had to test primes, okay? Because if the prime, like if 2 won't divide it, then neither will 4, 6, 8, 10, right? If 3 doesn't divide it, no multiple of 3 can divide it. So that leaves us with only the primes, okay? The next thing that we looked at though, is I had said, and like I have a little thing here where I'm showing like the factors of 36. Okay, and I want you to notice, factors come in partners, right? Now 36 is called a perfect square, which means if I took 36 cubes, and I actually showed this in class with 16, if I took and made a rectangle with it, I would literally be able to make a square, okay? But we always have one partner less, one partner greater. So we always have a little partner and a big partner, except when the partners are the same, and that's the perfect square, okay? Thus, that becomes the answer to the question we started class with. Can you have an odd number of factors? The only way that's possible is if you have a factor repeating, right? A number partnering with itself. Well, that only happens if you have perfect squares. Okay, so that is something that we wrote down over here. Let me not give it all away yet. So that I can go quickly, I'm going to just tell you, if you're sitting there at home, pause the video, write this down. Okay, but I'm going to keep moving because I've only got 20 minutes to make this video. Okay, but these are our perfect squares, right? 1 squared, 2 squared, 3 squared, 4 squared. Up to, and I went up to 10 square, okay? So anyway, I was asking students to try to figure this out. Now, where the here's where I go, okay? We know that we don't have to keep testing divisors of 269. We don't have to keep dividing through like the 260s, right? We can stop somewhere. And a student in class the other day said, you stop at the halfway point. Right? And they said, well, isn't the halfway point like divide by 2, so about 135? And I said, no, you can stop sooner. Okay, so I want you to pause the video and look at this and tell me when you think you could stop. Look at the divisor, look at the quotient. So none of these quotients are whole numbers, so therefore it's not divisible because you have to get a whole number, right? When you divide to be considered divisible. But pause the video and think about it. Where do you think you could stop? For students in class, I surveyed them. I had them put it in the chat if they were home and said, where do you think you could stop dividing? All right, so pause the video and think. All right, now if you're back, I did this. And then this, everybody got it as soon as I did this. I pointed out here the whole little partner, big partner thing, right? Little partner, big partner, right? All of a sudden we switch. we switch and go from big partner to little. So if I didn't have a little partner, I already tested all the little numbers, I'm not going to find a bigger number that could match up to it. All right. Therefore, as soon as I make this transition from little partner to big partner to little partner, I know I am done testing. Okay, so that's great news. For this problem, I actually didn't even have to test 17. Okay, so now here's the question. How would I know that? How would I know where that point is? And again, pause the video and try to think about it. How do I know what the point is where I'm going to switch from little partner to big partner? Okay, and this kind of helps you right here. That should help you. I did have one person figure it out today. I was very pleased, right? Because I wasn't really expecting a lot of people to get this. Oh, wait, the answer's at the bottom, isn't it? Yes, the answer's at the bottom. So, but I hope that makes sense to you, right? That what we have to do is take the square root. That's when the two partners are the same, right? When I take the square root, those two partners are the same. And so at that point, that's where I switch from little partner to big partner. Okay, so here's the rule that I have to test all primes up to the square root. All right, so I only test the primes and I only have to test up to, so that's why I didn't even have to test 17, right? I was done with my work right here at 13, okay, because 17 is greater than the square root, and that's why I saw it switch from big to little partner. So here's some other things that we wrote down. Okay, so we answered this question about the perfect squares having an odd number of factors. All right, we wrote this down. Factors come in partners where one partner is less than or equal to the square root and the other partner is greater than or equal to the square root. All right, and then I answered the all-important question, what will be on the test? Okay, so on the test, I will very likely give you a number like 571 and say, what divisors would you have to test? Okay, if you want to know if it's prime, what would you have to test? Okay, and if you miss even one number or you give me one extra, you're going to lose a third of the points. Okay, as soon as you make two mistakes, you'll lose like almost all the points for a problem like this. Okay, so you don't want to put in any extra values and you don't want to forget any of the primes. So first thing you would take the square root and then test all primes and just list them out. And some people say, well, I'm not going to put 2 because I just see that it's not even, but that's still testing for 2. And the same thing for 5, right? When you look at the last digit and say, well, it's not divisible by 5, you still tested 5 by checking that last digit. So you still want to list them. Okay, so you list every prime number up until you get to the square root. Okay, and a student asked me in class, like, would you make us like divide them and see? And I don't want you spending your hour on the test just doing busy work. But here's what I want you to notice. I want you to notice that it's labor intensive to determine if a number is prime, right? And to find its divisors. Because look at this, like this number, it's not that big, right? 9,083. If I take the square root, I get 95, right? Which means that whole little paper you did where you were like crossing off and then we circled what was left, all those primes from 2 to 100 that we found the other day, you would basically have to test every divisor in that list. There's no magic formula to make that an easy, quick thing to do. You just have to test and see if those numbers divide. All right, and so that is going to lead us into what we're going to talk about next week. When you come back to class on Wednesday after the test, we are going to be able to do that lesson on encryption, okay, and how prime numbers and factors, how that all plays into cybersecurity. All right, and so it is related to the fact that it is hard to factor big numbers. It's hard to figure out. It's labor intensive to try to find divisors of really large numbers. So anyway, this is where test 1 material ends. And then the next thing we moved on to, we started looking at divisors. Okay, and I asked the class to figure out if we divided by 7, right? So we did this. I said, what are the possible remainders when dividing by 7? Okay, because remainders are actually going to have something to do with what we're going to do next week with the encryption and the cybersecurity. Okay, so I told everyone in the class, pick a different number, pick like a smallish number, like you know, in the 20s or something, divide by 7. Look at all the remainders you get. All right, and then I went around the room and some people got 0, I got 0, got 3, got 5, got 1. Could I have a remainder of 8? Right, and we looked at this. If I think I have a remainder of 8, I don't, because I could go in an extra time. Right, so I'm not going to divide by 7 and get 8 as a remainder. That would mean I could put 7 in again. Okay, so we said this about remainders. When dividing by n, I can get a remainder of 0 through n minus 1. And then we started on a little side trip, okay? Because we need to talk about remainders to get to next Wednesday's topic. But while I'm on this topic, it kind of fits to be talking about changing fractions into decimals. So we start looking at this by going to this handout that I had told everyone to print. All right, and what we started to do here is each square, each whole square represents one whole. Right? That means each column represents 0.1 and each individual square represents 0.01, 100 and 1/10. Okay, and so then we started looking at shading these. I think I shaded darker on this one. Let me show you this one. Okay, we started shading these. And so here, 0.25, that's 2/10 and 5/100. Okay, so I shaded 2 columns for tenths, shaded 5/100, and then I showed how this is divided up equally into fourths, and I have literally shaded 1/4 of the square. Okay, thus the fractional equivalent to 0.25, as we all know, is 1/4. And so I don't want to give these away because a lot of these we've figured out in class, but we came over here and we started writing these down, right? These decimal equivalents. Okay, and so then on the back, okay, we worked along very happily at first, okay, where we looked at 0.5, okay, divided in half, right? That would be 5 of these columns. Each column is a 10th, 5/10, 0.5, right? Then we looked at taking the diagram and dividing it up into 10 pieces. Well, if you divide it up into 10 and shade 3 of them, that's just 0.3, 3/10. And then we divided the diagram up into fifths. Right, and so I told students to go to the front page. I was trying to block the answers from you. I hope you weren't able to see them. Go to the front page with fifths, and without using a calculator, just based on what you did here, right? 2 of my fifths, so every fifth is 2 columns, right? In other words, every fifth is 0.2, right? So 2/5 would be 0.4, 3/5 would be 0.6. So we went along very happily. You know, we shaded 3/4. We realized that would be 75 of these shaded in, right? Or 0.5 plus another quarter, 0.25. And then here's where we ran into issues. We got to 1/3. Okay, and so I said, okay, envision that there's 3 people who I have to give stuff to. Okay, I would divide this up by 3. I'd have my tenths, okay, my columns, and I'd say, okay, there's 3 of you, everybody gets 3 columns, everybody gets 0.3. Okay, but then I'd have this column left over at the end. Right, so I'd take my leftover column and I'd say, okay, well, let me divide that column up into 3 pieces. So I'd give everybody 3 columns, then I'd give everybody 3 squares, okay, 3 hundredths, okay? But then I still have a leftover 100, okay? So what I did there, it's almost hard to see it because it's so tiny, I have to subdivide that by 10, okay? So when I do that, that becomes thousands. And I'd say, okay, well, there's 3 of you sitting there. I've got these 10 pieces. All right, each of you get 3 of the thousandths, but then I still have a little piece left over, right? And this process is going to go on and on. That's why I've got this dot, dot, dot here. It goes on and on and on forever. Okay, so that's how I get 1/3 is 0.3 repeating. We tried this with the 9th, so I told everyone to try this on their own. So maybe instead of looking up, you already see the answer. Try that with the 9th. Think about having the 10 columns, but 9 people sitting there. How much would you give each person? Okay, so pause the video and try that if you didn't already peek at the answer. Okay, but what would happen is there's 9 people sitting there. First, you give everybody a 10. There'd be this leftover column again, right? That leftover 10. So you'd say, okay, there's 9 of you. I've got these 10 pieces. Okay, all of you get 1 of these hundredths. All right, so each person got a 10th. They got a 100th. 1 left over, so I subdivide that by 10. Every person gets 1,000. But I'd still have that little leftover piece. I'd subdivide that by 10, give everybody 1. There'd still be 1 left over. And so this is how I can see that 1/9 is 0.1 repeating. So finally, to end the class, we went back to the front page because I said scribble these out because I actually was doing this for my this handout's for my math concepts for elementary ed, where I'm teaching people how to be teachers. And so with you guys, I'm doing slightly different things. So cross those out and let's represent 1/7. Okay, so again, I have these 10 columns, 7 people who want stuff. Okay, so I give every person 1/10. Okay, then I have 3/10 left over. All right, which means I actually have 30 pieces there, 30 hundredths. Okay, so I say, okay, I've got 4 or 7 people sitting here. I've got 30 of these squares. Okay, fine, then everybody gets 4 of them. But wait a minute, I have 2 left over now. Right? And this is not very fun. Right? This is not fun at all to have 2 pieces left that I have to figure out how to divide up by 7 people. All right, this is definitely not going to work out nicely. And so what we're doing, the plan for Friday is on Friday, I have probably about 20 minutes left of this lesson that I'm going to make a video for. And even though Friday we are normally asynchronous remote, on Friday, I'm going to make a Zoom meeting from 9:30 to 10:20, and I'll be sitting there to answer questions from the review sheet. Okay, so if you have any questions on the review that I posted for the test, pop in on Friday. That's optional. And then watch the 20-minute remaining lesson video. So I appreciate you hanging in here for this quick summary of today's class, and I hope I was able to give you the information that you need.